So yeah, I'm going to talk about not representation of, but representation zeta functions. So there's you must have seen some special cases of this kind of a thing. So suppose you have a sequence, then you can try to understand properties of the sequence by constructing a kind of generating function. So this is called a Dirichlet's this is called a Dirichlet generating function. So it's just your sequence is an, so you're trying to count something that's indexed by n maybe, and the Dirichlet zeta generating function is just an by n to the power s. So it's a function in this variable s, and these kind of functions, they have so it's an infinite sum, so you should ask whether it converges or not. And they have a behavior that there's a line in the complex plane to the right of which they converge, and that's called the abscissa of convergence. And it turns out that the growth of the sequence can be captured by this abscissa of convergence. So if the sequence grows polynomially with degree alpha, then the abscissa of convergence will be about alpha plus 1. So I mean, I guess you've all seen this probably. The Riemann zeta function is the primordial example of a Dirichlet generating function. It's just a sequence where all the terms are equal to 1. And the unique factorization of integers tells you that this zeta function has a factorization into what are called Euler factors. So this was discovered by Euler, and so it has a product decomposition over primes. This basically just comes from the fact that every integer has a unique factorization into prime numbers. And this one converges for a real part of S greater than 1, which is maybe an exercise in calculus when we study convergent series. Now I'm going to introduce something called a global field. I'll come back to that in a minute. So there are all these, but you can think of maybe the rational numbers. So if you have the rational numbers, there's a thing called the Dedekind zeta function, and this somehow captures some information about this field. So when you take this to be the field of rational numbers, this is just going to be the Riemann zeta function. But there are other fields that number theorists are interested in, such as the field of Gaussian integers. So you just take Gaussian numbers, you just take rational numbers a plus ib, you just take numbers of form a plus ib where a and b are rational numbers. That's a field. And you may want fields where roots to certain equations are included. So you want to look at things bigger than the rational numbers, and those are examples of global fields. So the Dedekind zeta function of the field Q is just the usual Riemann zeta function, but there are some other kinds of fields which arise in algebraic geometry. So if you look at a finite field FQ, and then you can look at rational functions in one variable with coefficients in that field. Now that is interesting in algebraic geometry because it is the field of rational functions of the simplest algebraic curve, namely the projective line. So these are called function fields, and so you have algebraic extensions of Q, that is you take Q and enlarge it a bit to include roots of equations, and algebraic extensions of this FQT. These are what I mean by global fields. So they all have zeta functions, and this one is also very easy to compute. So if you try to compute the zeta function of FQT, so the zeta function has this thing that you must take a sum over all non-zero ideals in the ring of integers, so whatever that means. But here, so these are rational functions, so there's an analogy between rational numbers and between integers and polynomials. That analogy, if you take it, rational numbers correspond to rational functions, and this Riemann zeta function is related to just counting integers, so to speak. This one is related to counting monic polynomials, and it ends up having a very nice and simple, it's actually much simpler than the Riemann zeta function, right? The Riemann zeta function is something much harder to understand, but this is very simple. It's just given by this very simple formula. But what is surprising here is that this converges again for S, real part of S greater than 1. So we see the same behavior of the zeta function whether you associate it to a number field or to a function field. And so in general it's known that the Dedekind zeta function of any global field has abscissa of convergence 1 and can be extended to a meromorphic function slightly to the left of that. So it will have poles to the left of that, but you can extend it slightly with poles, and beyond that we do not know what happens. So now we are going to look at certain other, so I said this Riemann zeta function, Dedekind zeta functions, these are special cases. Yes, S is a complex number.
So it goes from C to C?
Well, it may not converge, so then,
okay,
yeah. Yeah. So, and then even if it doesn't converge, you can try to extend it by analytic continuation to a slightly larger region. So there's the region where it converges and then you try to extend it. So, so now there's been some interesting developments that suppose you have a group G, then we try to realize this group in vector spaces, and a representation of a group is irreducible if you cannot find a subspace of that vector space which is invariant under the transformations in that group. And so those are irreducible representations, and counting irreducible representations of a given size tells you something about the group. So now the representation zeta function of this title is this zeta function where an is just the number of irreducible representations of G of dimension n. So you can just rewrite this as sum over all irreducible representations of whatever dimension 1 over dimension of rho s. And the problem that we have that we are working on is for an interesting group G, what is the abscissa of convergence of this zeta function? So I need to explain what is an interesting group. So there's this class of groups, most familiar groups that physicists work with and so on, they are actually locally compact groups. And these groups have a natural sort of notion of volume which is called the Haar measure. And a lattice inside a locally compact group is a subgroup that is discrete, so its points are separated from each other, and it has the quotient space has finite Haar measure. So a simple example you can think of is R squared, which is a group under addition, and Z squared is a lattice inside R squared, right, the integer points. Because they are sort of scattered all over, and a fundamental domain for the integer points in the real space is just a square, and that has finite volume. So that's what I mean by the quotient space has finite Haar measure with respect to the notion of volume that you have on the group G. And there's a deep theorem of Margulis which says that that lattices are basically something called arithmetic. So for a nice class of groups. So semi-simple Lie groups of rank greater than 2. So you can think of SLN where n is greater than or equal to 3. So if you look at SLNR where n is greater than or equal to 3, then you have, this should be SLN inside SLNR, n greater than or equal to 3. And this is sort of the number field case, and the function field case is SLN. So you just look at n by n matrices with determinant 1, but the entries are now polynomials, and you think of it as sitting inside this sort of weird group of whose entries are that's another typo, Laurent series in the variable T inverse. So anyway, this is the important side to keep track of, SLNZ and SLN of polynomials. So these are the groups for which we would be interested in understanding the representation zeta function and the abscissa of convergence. So, so there's a conjecture of Larsen and Lubotsky which says that if you have two irreducible lattices in a group of rank greater than 2, then the zeta functions must have the same abscissa of convergence, saying that different lattices will somehow still have the same rough behavior in terms of representation theory. And to approach this problem, one uses Margulis arithmeticity. You need to somehow get a grip on what these lattices are, and Margulis's arithmeticity theorem tells us that we can realize these groups as some sort of products of groups, which I'll come to in a moment, G of OS. So you have this field, you have this lattice, and so you have this lattice, and what you're going to show is that this group has some sort of product decomposition. Not important at this point, but understanding these factors is the key to proving the conjecture. So we need to understand these local zeta functions. So let me give you an example. So if you want to look at SLNZ, then the local group will be SLN of the p-adic integers. So these p-adic integers are some sort of compact completion of the integers, focusing on phenomena that happen at the prime p. And and you can also look at power series in a finite field. So these groups are sort of limiting cases of finite groups. SLNZP is this pointer is not working. Anyway, SLNZP is a limiting case of the groups of integers mod p to the power k, and SLN of the power series is a limiting case of polynomials mod t to the power k. So these are limiting cases of finite groups, and finally we need to understand the representation theory of these finite groups. So the main difficulty in this kind of work is that we may understand the representation theory of SLN over a finite field, but these rings, the representation theory is wild. So there are some technical conditions, field of characteristic 0, and the Larsen-Lubotsky conjecture was proved for groups of rank 2. So basically these are groups SL3, SU3, SL1 over a division algebra of rank 3 and SU1 of a division algebra. So this was proved using p-adic integration techniques in 2014, and they also proved it for all higher rank groups, but the operative word here is characteristic 0, which means the fields that come from rational numbers. 10 minutes up. Okay, so I have just one more slide, which is, so we have these two groups, SLN Z mod p to the kz and SLN fp mod t to the k. So these are different groups of the same order, but they are not isomorphic. Do they have the same class equations? That's not known, but for k equals 2, this was proved by Pooja in her PhD thesis. Do they have the same representation zeta functions? For n greater than 3, this is an open problem. So in recent work with Urion and Pooja Singla, we were able to show that these local factors, these two kinds of groups have the same representation zeta functions, and using that we were able to extend the proof of the Larsen-Lubotsky conjecture to groups of rank 2. So with positive characteristic. So
thanks, Amri, for this nice talk.